We talk about nanomaterials and bioplastic from porang. Porang is a plant, Amorphous muleri, which can be used for, for replacement of traditional conventional methods fossil fuel polymers, and the work is published in recent number of agritech and the cooperation uh, leadership of Andri Pratalaba of University of Lampung. The plastic waste and which is enormous trouble and depletion of fossil fuels requires new methods for production of bioplastic, which wouldn't be so toxic and so like traditional one. The substantial accumulation contributes to environmental pollution, so its resilience against microbial degradation poses a significant challenge. Bioplastic would be biodegradable, which diminish reliance of synthetic plastic. Starch emerges as prevalent primary component in the production of bioplastic, owing to its array of merits, including renewability and cost-effectiveness. The application of nanomaterials to bioplastic is believed to accelerate the degradation of bioplastic. Therefore, this study is to identify characteristics of nanomaterial from product and obtain bioplastic. The method includes extraction of porang nanomaterial through a specific water-to-porang ratio of 2.5 to 1, followed by sonication in 50 watts and 75 minutes. The bioplastic formulated involve amalgamation of cornstarch, porang material, and glycerin. The chemical properties will be starch, amylose, ash, and calcium oxide. Now they check the effect and characteristics of such materials, because packaging, spoons, forks, and all needs the generation of waste in world, 381 billion tons of plastic of waste are produced every year and will be double in 2034. In Indonesia is a second contributor, ranking behind China, contributes 187 billion tons of plastic waste into its water. The surge in waste production equates to a staggering 38 million tons per annum, with 30% of this quantum constituting plastic material. Plastic exerts negative effects on the environment by reducing soil fertility, polluting the sea, and burning plastic waste also causes global pollution, global warming, as well as producing hydrocyanide and carbon dioxide. The problem is length of time for the composition of plastic waste by microorganisms found in the soil. Consequently, the generation of this waste is imperative to drive innovation by developing plastic derived from natural materials, a category commonly known as bioplastics. Starch, a prevalent natural polymer, stands out as a key candidate for the fundamental material used in bioplastic production. The widespread utilization across industries is significant in this context. In addition, the industrial demand peaked 25 billion tons in 2012 and is increasing. The main application is currently 60% for food processing industry and 40% in non-food industries such as chemical, pharmaceutical, paper, textile, cosmetic, and other industries. Starch as biomaterial has attracted much attention due to its following advantages: easy to obtain, renewable, less expensive, non-toxic, and easily degraded. As a raw material for bioplastic, natural starch has weaknesses, and modification needs to be made for better strength. Alternative effort to improve the characteristic of starch is increase its added value to modify it in nanoparticle size. Irawan et al. Reported that nanotechnology is a cutting edge. For many purposes, starch nanoparticles are from 1 to 1000 nanometer and can significantly improve the characteristic. Therefore, it has low suspension viscosity and a relatively high concentration with high binding strength due to its large active surface area. The production has been widely reported for various agricultural commodities, including breadfruit starch, cornstarch, and cassava starch. Porang amorphalus mulleri is a rising commodity in Lampung, currently getting attention from industry practice due to glucomannan content. The production of glucomannan from porang also is starch, as by its weather, and has potential to be used as bioplastic. In addition, no reports or studies have been made from porang tubers and application as bioplastic for food packaging. Their specific objective was uncertain. The existence of starch nanoparticles derived from porang tubers subsequently employed in the development of prototype bioplastic. The material is the main material used in the study was yellow porang tubers harvested in April after 7 months of growing. Subsequently, the porang was transported to laboratory packed into gallon sacks. Other materials used were maize starch, glycerol, and aquadust, and other chemicals for animals. The equipment used were digital ultrasonic cleaner with ultrasonic power 50 watt, particle size analyzer, scanning electron microscopy, X-ray diffractometer, blender, digital caliper, and other glassware for other preparation. The preparation of nanomaterial from porang was carried out by extraction and solidification process. The porang was peeled, washed with clean water, and removed any contaminants. Furthermore, it was soaked in water for 1 hour, then homogenized using a blender with ratio of water to porang 2.5 and 1, and then filtered and precipitated. After the precipitation process, the precipitated part was separated and over-dried at 50 degrees for 12 hours. The material was then filtered and sieved at 100 mesh to obtain flour form. The sonification process was carried out according to Bell-High et al., with modification of sonification temperature. The flour was placed in a 50 milliliters beaker glass with 1.45% concentration and immersed in an ultrasonic bath at room temperature, 25 degrees, operating at frequency of 40 kHz and a power setting of 50 watts and for drying for 75 minutes. Subsequently, the suspension was dried in a drying oven at 50 degrees for 2 hours and proceeded to particle size analysis. The dried form proceeded to chemical properties analysis: ash, moisture, starch, and amylase, calcium oxalate content, micrograph with scanning electron microscope, and identification of material phase and composition with X-ray diffraction. The bioplastic was prepared by application of the solution caustic with modification containing mixture of corn starch, porang material, and glycerol. Corn starch 10%, Pork material 5% and 5 milliliters of glycol were mixed in bigger glass, and then 100 liter of water was added. The mixture was heated in a magnetic stirrer at 70 to 80 temperature degrees and stir until the solution become viscous before casting in a glass plate. Subsequently, the glass was placed at room temperature until the film was frozen and released to proceed with thickness measurements. The thickness of bioplastic was measured on 5 different spots using digital micrometer under free replication. The chemical properties of polymer materials were investigated, including amylase, starch, and protein contents. So the chemical starch was percentage was 42%, amylase 14%, moisture 8%, as well as ash and hydroxyl oxalate 3%. The amylose content affected the properties, with higher amylose content increasing the strength and elongation of bioplastic. Moisture content was lower than only starch and was higher, which produced a moisture. And the difference was mainly affected by drying methods. Elevated temperature, extended drying duration also yielded reduced moisture content. The regulation of temperature during drying process was imperative to attain the targeted moisture level. The ash content was higher than clean corn starch, resulted from and calcium also was higher, 41%. This was caused by removal of the water was reduced. This was caused by removal of water part of the precipitation result containing water-soluble oxalate during the extraction process. Properties of pork materials were analyzed by using particle size analysis to determine the particle size distribution, scanning electron microscopy to observe the microstructure, and X-ray diffraction to analyze the phase and composition. The result of particle size distribution and microstructure is shown on figures. The particle size showed that the pork material has ranged from 1,200 to 4,100 nanometers, with average value of 1,404 nanometers. Moreover, it was bigger than pork materials with a range of 600 to 900. This result showed that the exfoliation treatment can reduce the particle size from micrometers to nanometers. Affirmed that particles falling in the nanometer scale ranging from 1 nanometer to are commonly referred as nanomaterial particles. That ultrasonic waves induced during the sonication process give rise to cavitation bubbles within the solution medium. Cavitation break particles into small sizes during processing. Based on the comparison particle size reduction depends on sonication power and duration. The microstructure of materials show that generation of cavitation bubble has impact in granules produce smaller particles. The round granule structure was identified as structure, and after sonication, it led to disruption and changes in the shape of the granule. The pork starch was severely deformed and formed a crystal-like shape after sonication treatments. The ultrasonic energy was trapped by the dispersed granules, which produce high-frequency vibration and destroy starch granules. The little form indicates the presence of calcium oxalate, which interacted with pork starch. The presence of calcium oxalate resulted in lower solubility of starch in water, value since the material was insoluble in water. The statement was supported by that oxalate had two forms based on its solubility, namely soluble oxalic acid and non-soluble form of oxalate. The X-ray diffraction spectrum detected highest peaks at 15, 38, and 40, 24 degrees with intensity values from 49 to 100%. Phases were observed, and the main phase were calcium oxalate hydride with monoclinic crystal structure, and the analysis results showed that the porang nanomaterials extracted contains calcium oxalate crystals. The findings supported the results of observation of nanomaterials. Plastic from cornstarch, porang nanomaterial, and glycerol has a brownish transparent color and formed a thin plastic. The development of browning hue in the bioplastic is attributed to the heating process, which induces a non-enzymatic browning phenomenon influenced by the inherent color of the constituent material. Since porang nanomaterials possess a brownish tint, the characteristic extend to the resulting bioplastic. The thickness was quantified using a digital microliter, revealed a range spanning from 0.23 to 0.39 millimeters with average measurement of 26 millimeters. The thickness was surpassed the maximum of 0.25 as standard bioplastic thickness. Starch thickness increased in higher concentration of bioplasticizer. The cornstarch bioplastic thickness increased from 0.18 millimeters to 0.26 millimeters with different plasticizer. In conclusion, the physical properties of porang were investigated, included higher increase of amylase, the better strength, and lower solid water solubility. Up to starch was 41, amylase 49, 8% of ash, and calcium oxalate of 2.5. The bioplastic had the form of thin brown layer with thickness varying from 0.23 to 0.39 with average of 0.26, and the particle size of nanomaterial ranged from 600 to 900 nanometers with average 700 to 22 nanometers. The further investigations were conducted for mechanical properties derived from porang nanomaterials, adherence, near complete adherence established for use and can be applied for food packaging. The assessment had significance due to imperative eliminating of oxalate to ensure stability of these materials for application with realm of food. So this is all. Thank you very much for listening to me.